Okay, so maybe we can get started. So hi, everyone. So welcome to join us for the Statistical and AI Methods for Health Data Science seminar series. The seminar series was organized by the StatsUp AI group. So this is an organization to try to organize activities that empower statisticians to participate more actively in AI research and then leadership. And then to let you know, so the StatsUp AI has been officially recognized as an ASA interest group. So here is the website for the group, and then you can find more information there, and then also sign up for the Google interest group, and then to receive emails. And then also we already post the first two seminar recordings on the YouTube channel of the group. So you can go to the website and then check for the first two seminars. And then we will upload all the seminars later as well. And then also just to give you a quick introduction about the steering committee members and then also the inaugural officers. Just to move on to our today's speaker, so it's our great pleasure to have Dr. Hernando Ombao to give us a lecture on the methods for characterizing brain functional connectivity. Hernando is a professor of statistics at KAUST and then also a principal investigator of the Biostatistics group. He's made a great contribution to the field in terms of making a lot of contributions in time series data and then also EEG data analysis. And then he is the founding chair, one of the founding officer and then 2019 chair of the ASA Statistical Imaging Section, the 2020 chair of the awardees of the awards committee of the COPS, and then also serves on multiple editorial boards in statistics and neuroimaging journals, and then also the co-founding editor of the new Journal of the Statistics and the Data Science Imaging. He is now currently also a permanent member of the study section on the Biostatistics panel of the NIH. He is an elective fellow of the ASA and then also the Institute of Mathematical Statistics. He also got the Mid-Career Award for Research Excellence at UC Irvine. Before I give it to Hernando, just to a couple of logistics. So for audience, sorry, I just couldn't find my cursor. For audience, so if you have any question, please type in the chat and then I will help monitor the questions. And then we will also have the Q&A time at the end of the session, the seminar, and then if you have any questions, so please raise your hand and I will call your name and then please unmute yourself and ask the question directly to Hernando. And then Hernando, please take it away.
Thank you so much, E, for the introduction. Thank you for everybody for being here. And so as like what E said, feel free to interrupt me if you have any questions, and I leave the monitoring of this to Yi. By the way, just a quick update on my membership of the NIH Biostats panel. I have completed my service for I think 4 or 5 years, so I'm no longer permanent member, but I still serve as an ad hoc on one of these on either of the A or B committees. So let me share my my slides. Okay, so I believe you can all see it now. Okay. So today I'll cover some of the methods that we're developing at KAUST on brain functional connectivity, and this is primarily really using electroencephalograms. These are electrical brain waves that you record from the scalp. And this is joint work with primarily with my students, Mara Talento, Paulo Redondo, Malik Shahid Zilingma, and postdoc Sarbojit Roy. So this is a general introduction on this data and what we're interested in. So EEGs are observed brain signals that you record from many different points on the scalp. So it's massively large data because the number of time points can be in the order of hundreds of thousands, even to millions. The sampling rate can be as high as 32,000 time points per second. Although usually when we receive the data, they've been downsampled to about 1,000 hertz, 1,000 time points per second, or 500 time points per second, or 100 time points per second. But nevertheless, as you can see, you have very, very dense temporal measurements. So I denote here this x of Tn to be the observations across the entire space at time point t for a subject n. And one of the things that we have to do is to extract features from these brain signals. So I'm being very vague here about what those features might be. I just denote them as f in this case, f of x of Tn. Now, so these features could be spectral features. They could be features that you extract from fitting a time domain model, and so on. So generally, just features that you extract from brain signals, from the EEGs. And Yn is the outcome of interest. And we would like, so some of these might be cognitive score. This could be reaction time, the time it takes for a subject to react to a situation. And we'd like to be able to model how these outcome of interest, Y, may be related to the features that you extract from brain signals. So trying to find a mapping between EEG, brain physiology, and behavior or other clinical outcomes. So in this talk, we will focus on three different approaches that we're developing. With primarily, we'll focus on the first one. Okay, and this is the KENCO. This is the Kendall-style canonical coherence, and this work is led primarily by student Mara Talento and postdoc Sarbojit Roy. Next, we'll cover the work of Paulo Redondo and jointly with Rafael Huser on spectral transfer entropy, STE. And then finally, we'll just give you a little bit of an overview about deep learning in Granger causality. So I also have a presentation in the next few weeks at the Bayesian on Parametrics in UCLA, and that'll be the focus of my presentation there. So Kendall's canonical coherence. Okay. So as I said earlier, we have EEG data that you collect from many, many channels, about 256, typically 32, 64, 128. And the number of time points can be very large, 10,000, 100,000, a million, possibly even more. Now, one of the things of interest is that how do we model association between two groups of channels? Let's say the anterior channel and the occipital channels. So we may be interested not only in looking at dependency between different single channels, but rather looking at the collective effect, collective activity of a particular region, and looking at the dependency of that with the collective activity in another region. Okay? So region to region type of a dependence. So you've also seen this in fMRI, where you may model voxel to voxel connectivity or region to region connectivity. And very often within a region, which consists of thousands or tens of thousands of voxels, the first step is to reduce dimensionality by summarizing activity in each of those regions. And in fMRI, you take averaging and so on. In EEGs, that can actually introduce some problems. And so we will go over these limitations. So with Kendall's canonical coherence, as I said earlier, our focus is to model dependence between a pair of regions. So it's regional rather than channel specific. And moreover, we would like to look at frequency band specific dependence. So rather than looking at how does a time series in region X, how is that dependent with a time series in region Y, we'd like to find the frequency oscillations that drive that dependence. And so I'll give an overview on that. So the first talk, as I said, is in Kendall's canonical coherence. The second is on deep learning approach to assessing Granger causality. This is the work of Malik Shahid. So you're looking at how the past of X1 and the past of X2, how that might actually predict the present of X1 and X2. And you go through these neural networks. And so the idea is that you want to be able to express the present of y, the present of x and the present of y, as some function of the past of x and the past of y with these weights that you'll have to estimate from this neural network. So the third topic is at a spectral transfer entropy. So I'll give the description of that later in the talk. So first is on spectral dependence. Okay? I already mentioned that we're interested in looking at dependence between oscillations. And so this is the starting point of that framework. If you have xt and yt, suppose that this is jointly weakly stationary, you can express xt and yt in terms of a basis, the Fourier basis. So these are the complex exponentials. These are the sines and cosines at different frequencies omega. And then now you have this. This is the random amplitude that you associate with every basis function. This is the amplitude for x, and then this now is the amplitude for y. Okay? Now, formally, if you're familiar with the books of Brillinger, as well as with Shumway and Stouffer, as well as with Brockwell and Davis, then coherence between xt and yt at frequency omega is defined to be the modulus square of the correlation between these random amplitudes. Okay? And so modulus square. So this is the classical definition of coherence. And so when I was starting out as a student, this did not really make a lot of intuitive sense for me. And so I tried to find ways on how to explain this to myself so I can actually understand it. So if you can, you can also take a look at this. So based on that motivation for trying to understand more what that means, we can look at the covariance between x and y as a covariance between this decomposition or this Cromere representation. And it turns out that under stationarity, the covariance between x and y is equal to the integral of the covariance between all of these random amplitudes integrated across all frequencies. So for every frequency, you have a covariance between the random amplitudes for x and the random amplitude for y, and the covariance between xt and yt as a whole is now the sum or the infinite sum of all of these covariances at all frequencies, okay, under stationarity. And so now comes the question: if there is a covariance, if the covariance between x and y, let's say, is large, quote unquote, large relative to its variances. Now, the question to ask is, what are the frequencies that account or that contribute the most to that covariance? So that's one of the questions that we will try to address here. So developing this intuitive point of view of coherence and thinking along the lines that the covariance between xt and yt can be decomposed into the covariance between all of these random amplitudes, then we can consider one particular oscillation in x of t. So this is the x of t oscillating at frequency omega. It is this. Recall now that x of t itself is the integral. You're adding all of these across all frequencies. Okay. But for a particular oscillation, we have this. This, as I said, is that function. You can think of it as a basis function. And this is a random amplitude. Okay. So x of omega t is the omega oscillation in xt, and the y of omega t is the omega oscillation in y of t. Now, we will show here that the correlate. So if I take a look at these two oscillations, I take the correlation modulus square between them, that turns out to be the same as coherence. Okay? And so we go through a little bit of these details. Now, the variance of x of omega t is exactly this. Now, this part is non-random. You can take it out of the variance operator, but you have to take the modulus square of that. But the modulus square of this complex exponential is simply equal to 1. And so now the variance of x of omega t is exactly the variance of this random amplitude. And similarly, the variance of y of omega t is simply the variance of that random amplitude. So the covariance now between x of omega, the omega oscillation in x, and the omega oscillation in y turns out to be just equal to the covariance between their random amplitudes. And so therefore, the correlation modulus square of this omega oscillation in x and the omega oscillation in y is simply the same as coherence. And so this to me is a bit intuitive, because then I can find I can really it opens up the possibility of decomposing two-time series into some bases like the Fourier, like the wavelets, and therefore you can also examine dependence between xt and yt through these different decompositions. Okay, and if we focus on the Fourier, we decompose them across different frequency bands, then I can analyze, I can measure dependence between xt and yt, decompose that into the contributions due to the different frequency oscillations. So this work has been, we started with this work. This is with Sebastian van Bellegem, 2008, in IEEE Transactional Signal Processing, and recently with Marco Pinto, 2023, in ECOSTAT. And we have this paper called Spectral Dependence. It explains how this particular framework can be expanded into different types of dependencies under the spectral realm. So here is a very rough illustration. You have x of t and y of t. These are your two signals. You can decompose x of t into its low oscillation, low frequency oscillation, the middle frequency oscillation, and the high frequency oscillation. The same thing now with y. Okay. And so now dependence between x of t and y of t, between these two, can now be decomposed, can be expressed as dependence according to their low frequency oscillations, correlation modulus square, the same thing here, and then the same thing here. And so therefore, this now allows us to answer the question that if xt and yt are highly cross-correlated, they're highly dependent, you can now identify the frequency bands that explain or contribute the most to that dependency. So now with Kendall's canonical coherence. So here, the problem is that we have two regions, and you'd like to model dependence between these two regions, and you'd like to model that dependence according to their, according to the underlying oscillatory activity. Okay? So there are a number of approaches for finding, characterizing dependency between this region where you have these magenta colored channels and the brown colored channels. So one way to do that is by aggregating all pairwise dependence. Okay, so here is a particular channel. I look at its dependence between those. These are the two pairs, and some more, and some more. So you have all of those pairwise dependencies, and now you aggregate these measures according to some reasonable way of aggregation, looking at the median, examining the percentiles, and if you have many of these and you have many trials, so that can be done. Another is by, in fact, summarization. So you have many channels in one region. You can summarize activity in that region in some way. We'll go over some of those that's quite popular in the literature. And then now, based on those two summaries capture activity in each of those two regions, and therefore dependency between those two regions will now be captured by the dependency between the summaries in each of those two regions. Okay, so here is an example of that. We have these EEGs from the frontal, that's the blue, and then EEGs from the occipital, that's the red. These are the different EEG traces in those channels in the blue, and then this one is in the occipital area, and well, posterior area. And so now here you can summarize activity in the blue and in the red in this way. Okay? Now we have to be what we have to be very cautious about is that not all of the signals from the channels are in phase. There could be some phase lags between those two channels. And you can see here, the peak occurs early for one of the channel and then a little bit later for the other channel. But if you look at these two EEGs, they look kind of similar. Okay, that one is a shifted, some sort of a shifted version of the other. And once you have that situation, then doing a straightforward averaging, in fact, can lose that innate property of these signals. So we have to be very careful about that. In terms of, I already mentioned one way to characterize dependence between two regions is to aggregate all pairwise dependencies, and that's a bit too simplistic, and this, in fact, could be skewed by a few pairs. Okay? Now, a more common approach will be by summarization within each region. So this one, in a way, also achieves some dimension reduction. And we do that. One of the ways to do that is by taking some average or some measure of central tendency within each region. So that's one approach of summarization. The other is by principal components analysis. So these are the two common ways. Now, for fMRI, this seems to be a popular approach, taking the mean or the median at each time point across the thousands or tens of thousands of voxels. Now, both of these methods take on a form either that the summary in the Y region is equal to some weighted average of all of the observations of all of the channels J. But here the focus is that they're all contemporaneous summaries, meaning the summary at time point T is a function of the observed signals also at the same time point. Okay. And so here's an example on the right side of the screen where for a particular time point, you take the average of all of these, and then that's your summary, or take a weighted average. So here, WJ and WKs, in fact, this can also be estimated data adaptively. Now, another type of summarization is that the signal, the summary signal at in the Y region at time point T is a function of all of the observations, all of the channels in the Y region using the present, past, and future observations. Okay, so in the first summary, it's all contemporaneous. The summary at time point T is a function only of the data at the same time point, but you can expand on that and show and find these weights that are optimal in some sense, so that the summary at time point T is a function of Y of all of the channels in region Y, but at all the time points as well, present, past, and future. Okay. So I don't know if there's somebody in chat, but I think Yi, just feel free to interrupt me, if you'd like to raise a question. Okay. So aggregating within a region, one way to do it is by just taking the average. Okay, so the weights here, these are predetermined, and K is, if there are J channels in one region and K channels in another region, then I simply use 1 over J, 1 over K as the weights. Okay, so these in fact are fixed. They're not data adaptive. Once I know the number of channels, I know exactly what these weights are. So averaging within a region may work in fMRI because you don't have very strong temporal resolution, but it can be problematic in EEGs because some signals, as I said, are out of phase. Okay? So this is a cartoon where if my signal in channel 1 is this -1 raised to the T, so it's -1, 1, -1, 1, -1, 1, and so on. Okay. But on the other hand, if the signal at the other channel is a shifted version of the signal so by the way, this is Y1, this is supposed to be Y1 t minus 1. If it's a shifted version, then you have this. And so if you take the averaging, you get a 0. Okay, and clearly the zero signal does not represent these two, the activity in these two channels. So one is simply a shifted version of the other. And you can also see this in sines and cosines, where if you shift a sine and shift a cosine in some way, then if you take the averages, then you also get a 0. Okay? And in fact, one has to be very careful with that, because if here is an EEG. These are the EEG signals from a simulated driving experiment, and you'll see here that the on the right side, these are the channels on the right side of the temporal, parietal, occipital regions. You see here that these signals seem to be nicely in phase. Okay, so the peaks, the maxima and the minima, the local maxima minima, these peaks are occurring at around the same time point. So they're in phase. So this is during the drowsy phase, If you look at the alert, during the alert brain state, you see that they're no longer in phase. And so here you see that the peak in the blue is taking place later than the peak in the yellow and in the magenta. Okay, so there is that. So these signals are no longer in phase. Now, also quite really interestingly is that if you look at financial data, during a market crash, many of these stocks, in fact, are very, 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 very highly correlated. They all drop. So there's a very strong synchronicity during a market crash. But during recovery, then some stocks can recover much more quickly than the other, and they will not be in phase anymore. So it's in these drastic, negative extreme events when they are perfectly in phase. So now with respect to EEGs, in this particular example, this particular data set, we see that when the person is drowsy, so they're awake, but they're half asleep, half awake, you see that the signals on the right side of the temporal, parietal, occipital, they seem to be in phase, but when they're alert, they're not in phase. So if you do averaging here, then this could be problematic. If you do averaging here, I think it's fine. Okay, and so simple averaging, one has to be cautious about it, as I said, just depending on the situation. You may not see this in fMRI because, as I said, the signals have the temporal resolution is about one 3D image per second or per 1.5 seconds and so on. And so these types of imperfect alignment in time may not be a problem. So another way to summarize signals per region is via the notion of principal components analysis. And so the idea is that if you have a high dimensional signal x of t, you compress it by expressing this x of t into u of t, where q here is smaller than p. Now this u, the compressed signal, is a linear combination of the observed x of t, present, past, and future. So the idea is that you have a high dimensional signal, you compress it in some way, because I don't know what the optimal AJ might be at this point, but you want to compress this high dimensional signal into something of lower dimensional, so that when I reconstruct x of t using the low dimensional summary, this is the reconstruction. Okay, the reconstruction is a linear function of the compressed signal, present, past, and future. The idea is that you want the reconstructed to be as close as possible to the original signal in terms of this L2 loss function. So you want to minimize the squared error of reconstruction. So you want to find the AJ and the BKs so that this error of reconstruction is minimized. Okay, so this is the notion. This is the motivation for principal components analysis. Is you have signals in one region, you want to find a summary of those signals so that they're optimized in a way that if you want to reconstruct back your original signal, you minimize the squared error of reconstruction. So PCA, therefore, with PCA, you allow the data to tell you how you obtain your summary, how to obtain these AJs. And so PCA is better than averaging because it takes into account all the temporal shifts, because your summary is a function of present, past, and future. And they're also data adaptive. Okay, so you're letting the data tell you how to weight these channels according to present, past, and future. Okay, but we have to keep in mind, though, that the goal of PCA is to control reconstruction error. PCA does not take into account dependency between X and Y. It's blind to that. With PCA, you were in fact doing some eigenvalue, eigenvector decomposition of the variance covariance matrix in X, or the spectrum in X, and also the variance covariance function in Y, or the spectrum in Y. It does not take into account the covariance, nor the cross spectrum, nor the dependence between X and Y. It does not take this into account. Okay. And so now, how do we proceed improving on PCA, given that our goal is to model dependence between a big set of a region with a large number of channels in X and also in Y? So, well, in fact, our statistical forebearers, have already thought about this. Okay? So this is the canonical correlation by Hotelling about 100 years ago. Okay? And which takes a look at the relations between two sets of variates. And now Brillinger, even as early as the 1960s, already has written some proceedings papers on this for the frequency domain. And finally, this appeared in his book in 1981 on spectral analysis. So quite interesting for me. Actually, quite disappointing that whenever I see a paper in machine learning and data science that talk about this kind of summarization, somehow it gives you the impression that this idea was developed, just yesterday, a few days ago, when in fact, really, in 1936, Hotelling already did this. So a statistician already developed this 100 years ago. And so I think we really have to push back and on this and be more cognizant of our history, to be more respectful of the people who came decades before us who have developed these ideas. I think we have to give them credit for that. So Hotelling already have thought about how to deal with this problem. In fact, Brillinger already developed this in the frequency domain as well. And where we're coming from here is improving on this frequency domain canonical coherence of Brillinger. But we'd like to be able to robustify this metric, because the spectral matrix, cross covariance matrices are in fact quite sensitive to outliers. And so how do we obtain a more robust approach so that we have more stable results across different trials, different experiments? And this is the focus of the work of Mara Talento. Okay? And so this is the idea with this Kendall's canonical coherence. Okay, you have your multivariate time series. These are your purple channels. Multivariate time series. Again, these are your brown channels. And you want to model dependence between them. And our approach is to extract oscillations. I mentioned already before, you have the low, middle, high frequencies. So in EEGs, you have your delta frequency band. You have your delta frequency band. That's the 0 to 4 hertz. And then you have your theta. That's your 4 to 8. You have your alpha. That's your 8 to 12. You have your beta. That's 12 to 30. And then you have your gamma band. This is from 30 to 50. Okay. The endpoints can change slightly depending on which lab you are collaborating with, but this is more or less the nomenclature for these frequency bands. And so the idea now is you want to extract your delta oscillations in X and in Y, your theta oscillations, your alpha, your beta, your gamma oscillations. Okay? And just a very quick overview with respect to this linear filters is that you can, so for a fixed frequency band, now you can apply there are many kinds of filters. Butterworth filter is one that we use, but you have these filter coefficients. These filter coefficients at frequency omega is such that if you take the Fourier transform of those filter coefficients, take the modulus square of those filter coefficients, the modulus square, in fact, will have a peak and will have power that's concentrated in this omega band. Okay. Now, when you change your omega from the delta to the theta to the alpha and so on, then you also change the filter coefficients. Okay. So, there's one course on filter design in signal processing. But here we just went through this in 1 minute. But in any case, so now you have you want to extract your delta oscillations in X, your delta oscillations in Y. You apply the corresponding delta filters. So for us, delta filters coming from the Butterworth, you extract all those signals in X and also in Y, and then we apply, and then we study the dependencies between the delta oscillations. Now we look at the theta oscillations next, the alpha, the beta, the gamma, and so on separately. Okay? And so now we have these omega filtered oscillation in X. Think of them for now. These are your delta oscillations, let's say low frequency oscillations in X and the low frequency oscillations in Y. And the idea is, how do I summarize all of these in X? How do I summarize my omega oscillations in Y? How do I summarize them in some way? So that the summary optimizes some criterion. Okay? So for a given A and a given B and a given time lag, so for a given A, given B, and a given time lag, I can obtain the summary in X, the summary in Y. I can compute the correlation squared between these summaries. And so now I want to find my alpha, my beta, and my L, so that these alpha, betas, and L at a particular frequency band maximizes this criterion. Okay, so that's what we're trying to do here. And so so some details here. If we have if these oscillations X and Y have zero mean, they have the variance covariance structure as given here. You can define the correlation, the correlation between this particular summary and another summary, a summary in X and a summary in Y. You take the correlation between that, and for a fixed lag H, if I constrain for identifiability, if I constrain this quantity to be 1 and this quantity to be 1, you're kind of like normalizing within each region or standardizing within each region, then this boils down to maximizing this, this quantity. So this quantity now takes into account really the correlation between X and Y. So unlike your PCA, you're looking only at the correlation between the channels in the X region and also the correlation between channels in the Y region. Here you're looking at the dependency between X and Y itself, X and Y. Okay? So you want to maximize this quantity. It turns out that this has some dual formulation, okay, and which is also, I think, easy to understand. And so here you're trying to summarize the future observation in Y that can be best predicted by the summary of the current and past values of X. And so this, you can think of this from a regression or prediction point of view as well. You're trying to predict some summary of Y using some summary of X, of course, with these constraints. And it turns out that if you want to minimize this prediction error, then this prediction error boils down to, so this is your prediction error. You can expand that, and therefore Now, if you take the um, if it, now it turns out here that that minimizing this prediction error is the same as maximizing this quantity because of the negative sign here, and that is in fact related now to what we have formulated earlier with respect to canonical coherence. As a canonical coherence, looking at dependence between x and y, the vector x and the vector y can also be formulated in terms of this kind of a regression least squares error or L2 loss formulation. Okay? And here the solution is really, if you look at the Billinger papers, is simply to look at the eigenvector eigenvalue decomposition of this quantity. Okay, so the question here now is that, of course, this is known. This is known. All these within X dependency, within Y dependency, and between X and Y, all of these quantities are in fact not known. So they have to be estimated. And very often the estimates of those are sensitive to outliers. And so what we do is we characterize that dependency, in fact, using Kendall's style. Okay, so think about, you have these covariance matrices, spectral matrices, which you have to estimate. Instead of estimating them by your standard approaches, we estimate them using Kendall's style. Okay, that's really it. And so with Kendall's style, the dependency between X and with Y is now in fact modeled or characterized by dependency between the ranks of this X and the rank of the Y. And so therefore, this is robust against outliers, and it also captures potential nonlinear dependence between X and Y, which you will not capture using only covariance or correlations. So now I might also want to ask, what exactly are the roles of these primary eigenvectors, A and B? So the primary eigenvectors, in fact, if you take the magnitude of each element of that eigenvector, they in fact represent the weight that is associated with each of the channels within each region. And so therefore, you're able to identify which channels in one region and which channels in another region account for the dependency between the X and the Y channels. And so the dependency as a group in between X and Y, you can actually capture that dependency. You can capture the channels that account for most of that dependency through the primary eigenvectors. And so that's the role of this of these eigenvectors. So here is an example from an EEG. Okay, on the left here, these are now the delta waves. Okay, we apply some filtering on the EEG channels. So these are the delta waves on the occipital parietal region. So occipital is at the anterior, parietal is somewhere in the middle. So here, these are the occipital parietal delta waves. And this now is a frontal anterior delta. So you're looking at, if this is the brain, okay, we're looking at the regions at the back and also regions in the front. Okay, we're looking at delta waves only at this point. So you'll see here that the EEGs for the posterior, the occipital parietal, these are the EEGs, and if you do some naive aggregation, which is I'm looking at one channel here and another channel in another region, I take the correlation between them. I take the correlation across all of these different pairs, and um, um, sorry, no, backtrack. What we did here was that we looked at, for each of the regions, we took the average. We took the average of all of the channels in the posterior part as well as the channels in the anterior part, and we took the correlation between those at the delta band, so we obtain a coherence of 0.53 when we do that. When we do PCA, on the other hand, you see here that the shapes of the summarized waveforms are very similar with the naive aggregation and PCA. And in this case, coherence is at 0.48. Now, if we replace those covariance matrices, spectral matrices, using um, using the approach by Rousseau et al. This is another way of obtaining a estimate of the variance covariance matrix that's also robust. Then we obtain coherence of 0.7. But if you use actually the Kendall's canonical coherence, you obtain coherence of 0.78. Now, this is not a contest of which one gets the highest dependency value. So we shouldn't be comparing coherences that because Kenko gets the highest value, then that's the best, because Kenko is in fact designed to maximize that dependency. Okay, so we're defining dependency as the maximum dependence, maximum correlation between these two sets of regions. However, if you look at, in fact, the summaries of these, I believe that the Kenko aggregated one is more obtains a fidelity to the actual signal than the other summaries. Now, in another work by Zieling and Mara, which I won't cover here, is that they also, in fact, use these the primary eigenvectors, the way the brain network is organized, looking at which channels contribute the most, and they do that. They use that to obtain their fuzzy clustering across different brain states. Okay, which I won't cover now. Okay. So there are other examples of this Kendall canonical coherence using other data, but in the interest of time, I'll move forward, and I'll spend the next 5 minutes talking about this work by Paulo, and jointly with Rafael, who is his co-supervisor, my colleague at KAUST. And this is the idea. Okay. With Granger causality, you ask the question: does X Granger cause Y? Okay. And so how we can formulate this is that you take a look at the predicted value. We predict Y using its own past and the past of X. We define the prediction error of Y when we use the past of Y and the past of X. And this is the prediction squared error. Okay. We can also predict Y using only its own past, meaning I don't involve X. So you obtain a predictive value of Y using only its own past. And based on that, you obtain the prediction error, which depends only on its own past. And here, if the prediction error, when you include X, is smaller than the prediction error without X, then you say that X Granger causes Y. Okay, so this is the essence of Granger causality. Really, this knowing X, thus including X in my prediction, helped me to improve my prediction of Y. Okay? And so now this idea is generalized using transfer entropy. Okay, because this is only looking at prediction error. Okay, with transfer entropy, you're looking at, in fact, distributions, joint densities. Okay? So with transfer entropy, the idea is that if you have X and Y with this joint density, now that's the general way of characterizing what's in X, what's in Y, and what's jointly in X and Y. Now, when X and Y are independent, then we know that the joint factorizes into the product of their marginals. Okay? And so with entropy in Y is defined as the negative of the expectation of the log of the probability mass probability density function. And in fact, when Y is normal, when Y is a Gaussian distribution, the entropy in Y is a function of its variance. The variance measures the variance is a measure of uncertainty within the spread, the uncertainty within that distribution around its mean. Okay? Now, when Y is Bernoulli, entropy takes on this form. And if you actually plot entropy as a function of the probability theta, you see that entropy is maximized when theta is a half. Of course, when theta is a half, then you get the highest level of uncertainty. When theta is close to 0 or close to 1, then either you will always get heads or you will never get heads. But if it's close to a half, then there's a lot of uncertainty. Okay, so entropy measures the uncertainty in a system. You can also have the joint entropy in X and Y, and the conditional entropy in y given x. So when x is known, then what happens to the entropy in y? So this is in fact, this conditional entropy in y when x is known is equal to the entropy in jointly in x and y minus the entropy in x. And so this conditional entropy is a reduction of the uncertainty in x and y when in fact x is known. Okay. Now, if there's no reduction in uncertainty, then x does not contribute to the reduction in entropy. And this happens when in fact x is independent of y. And so with transfer entropy, the idea is that the idea is as follows. There is entropy in y when I know its own past. Now, there's also the entropy in y when I know its past and when I know the past of x. And when this entropy is in fact reduced, when knowing the past of x reduces the entropy in y when I know its own past, that this in fact is called the transfer entropy. Okay, and so this is more general, in fact, than just prediction. You're looking at joint densities here and conditional densities. Okay? And and that also is in fact related to mutual information. And so really in the interest of time here, I'll just say that we're using the notion of transfer entropy. We're applying this into the spectral realm. We're looking at how does the reduction of entropy, how is that taking place when you're looking at the delta, theta, and those different frequency oscillations. Now, the big challenge here is that when we look at this transfer entropy, we're looking at the Kullback-Leibler divergences. It's a Kullback-Leibler divergence between this general conditional PDF and this PDF when in fact y of t and the past of x are conditionally independent when y is known, when the past of y is known. So this is, in this setting, you have that when the past of y is known, the past of x does not give me any more additional information about the future of y. Okay. And so this is your null case of independence or conditional independence. And so with transfer entropy, you're looking at the discrepancy between these two densities, these two conditional densities. But then you're looking at this, in fact, looking at by considering different oscillations as well. And so because this now is a function of the densities themselves, then you'll have to estimate these densities. And how what Paulo has done is to model these densities, in fact, using copulus. And under this particular framework, he's able to obtain a very nice inferential framework under divine copula, because it's able to simulate the distribution of transfer entropy under the null hypothesis when you have the conditional independence. And so it allows for creating that reference distribution of transfer entropy so that under the null. So now you can actually test whether your estimate of transfer entropy falls within the tails of that distribution or in the center of the distribution. Now, very briefly on this Bayesian deep learning in Granger causality, this is the work. This is led by Malik Shahid, and as you can see here, the idea is that you have the past of x and the past of y as your inputs. You want to predict the future x of t and y of t. You have this neural network, okay, and so the idea now is that does y of t, does y Granger cos x. And the idea is that under the null hypothesis that it does not Granger cos x, then this tells us that I can perturb the past of y in however I like. Okay, I can perturb it by permuting blocks of time series, so I preserve the local autocorrelation structure. I can permute these blocks, and even if I do that, it will not have an impact on the predicted value of y, because under the null hypothesis, the past of x does not Granger cos y. Okay, and so this is the idea of Malik. So building this Granger causality in the deep learning framework. Okay. And so again, just the final reference here is that the first two methods are the first one, Kenko, is an archive. The second one is also an archive, and this will appear in the Annals of Applied Statistics. And I want to thank again Yi and the organizers for the invitation, and also want to end that there are the EEG statisticians are quite, I would say, less involved in the fMRI neuroimaging setting because they exist in a different different neuroscience world. But I want to point out who these personalities are, and this is only really a subset of the people. These are what came to my mind when I was preparing my slides. Emery Brown from MGH. For those of you who do not know Emery Brown is an MD PhD. He is an anesthesiologist at MGH, but he's also a statistician. He is a PhD stats from Michigan from many years ago, and he knows the science, he knows the math, he knows the stats. Really, you should be following his work if you're interested in this area. Ori Eden from Boston University, Rob Cass from Carnegie Mellon, Marina Vanucci at Rice, Sharon Wang at UCSF. Sharon Wang finished her PhD under Marina, and now she is studying to be a neurosurgeon at UCSF. Raquel Prado, UC Santa Cruz, Mark Fecas at Minnesota, Rob Crafty at Emory, Scott Bruce at Texas A&M, Alice Hodge at Washington, and Samanto Basu at Cornell. So this again is just a subset, of these people. Okay, I'm open to questions, comments, please.
Thank you, Hernando. I think there was a question related to the entropy for different distributions from Matt Ripple. Does log mean natural log?
Yes, it is a natural log. Thank you. Yes. Yes.
So for audience, if you have any question, please please raise your hand. And I will call your name. May I ask a question for, oh, sorry, David, go ahead.
Thank you, Hernando. That was wonderful. People have been looking at trying to understand what's going on in the brain for a long time now from many different perspectives. What would you say are the major steps forward in this space?
Yes. Yeah. One of the things where we're focusing on is in real-time processing, real-time monitoring. I think that where we're headed to would be more of these wearable devices. So we have this wearable device that truck drivers can wear to monitor their level of sleepiness as they work on the roads. Also wearable devices for BCI, brain-computer interfaces. So we have these patients who may be paralyzed and unable to move, and so unable to talk as well. And so perhaps using their EEG, can they dictate how their wheelchair can move from one direction into the next? And so the next phases will be trying to identify where we can find the most sensitive signals according that is specific to the task we have in mind. So trying to identify where in space we can find that, trying to process them very quickly. You're dealing with massive data here, trying to find the features in the signals that are very sensitive to the task at hand itself. So I think that this will be and then trying to bring in all available computing and modeling and estimating technologies from AI, from deep learning, incorporating that into this area. I think that's where we're headed.
Thank you.
Thank you, David. I think Aram has a question.
Thank you, Hernando, for a great talk. Okay, let me open my video. Yeah, I have a question. When you disaggregate into low and different like frequencies, right, and find for each this low or high, how do you aggregate back? That's my first question. And the second question is, so here you do not consider that low can kind of have some effect on high frequency, right? You look only on low and high separately.
Okay. Yes. So these are two separate and very good questions, Aram. The second question, you're looking at how does dependency, is there dependency between low frequencies and high frequencies? Okay. Now, under the framework of weak stationarity, there's no dependence between them. Okay, that's the model. That's not the data telling us, right? That's the model. Now, there's work by Loew in the 1950s called harmonizable processes, where he allows dependencies between different frequencies and different frequency bands. And there's already some work on harmonizable processes for EEG data. And we've done some work on this in 2017, Journal of Time Series Analysis, where we look at dependencies between low frequencies and high frequencies, for example. Now, the challenge there is that if you look at the variance covariance matrix, under stationarity, it's zero at all frequencies except for the diagonal when the frequencies are equal to each other. When they're not equal, as you can imagine, this becomes a very you have a much bigger parameter space to contend with. And so, but this one is you can still get good estimates if you have replicates in your data, which is so natural for EEGs. You have many different trials. You can incorporate information from those different trials to obtain the estimates. And so different frequency bands, in fact, yes, it's ongoing work. There's still a lot of work that has to be done, but this is being done. With respect to integrating back, there is a one-to-one transform. So if I have my frequency oscillation, I can go back and recover the EEG itself. Now, when it comes to prediction, for example, we can already use all of the different features we get from different frequencies and use that as inputs to our feature. If you want to predict behavior, decision making, and so on, you can aggregate all of these different features extracted to predict the outcome.
Thank you.
Welcome.
Okay, is there any other question for Hernando? Fernando, can I have a just quick naive question? So would you please give some like a biological insights or interpretation about the different frequency bands? So what like each frequency band may mean?
Yes. Good question, E. So with respect to the very low frequency bands, the delta, you see this to be more prominent when a person is drowsy or when a person is asleep. Now, looking at the higher frequency bands like the alpha, beta, and gamma, they're more they're quite expressed during cognitive tasks when you have to remember things, when you have to remember sequences, and when you're trying to analyze a problem, trying to remember your memory is being gamma that's actually active during those. Now, the theta is also present when a person is concentrating. The alpha again has a special it's quite special because for people who, let's say, who exercise in yoga and then they close their eyes, you'll actually see the alpha rhythm appear very prominently. For those of us who don't practice yoga, you may see it, but it's not very prominent. But for those who practice yoga, the alpha rhythm actually really appears very nice. So again, all of these different frequency bands have the mapping with respect to brain states as well as with behavior.
So then I have a follow-up question. So how can we interpret the variation in the coherence across different frequency bands between two brain regions? Does it
Yes.
relate to brain region function or something else?
Yes. So that's another really good question. Now, the one of the naive ways of modeling dependence is just forget about the frequency bands, right? Let's just take a look at transfer entropy and so on. And you may in fact obtain some dependency between regions that are active during a particular state that's not active during another state. Okay. However, this particular observation, in fact, may be quite broad in the sense that you want to look at what is the frequency band that drives that dependence. And so to me, it's just an added, it's a more specific information you can obtain. Now, now sometimes that dependency may be captured only, let's say, by the low frequency band, and it's very noisy. You won't see it in middle or higher frequencies. And so if I obtain the transfer entropy between X and Y, I may actually not see that. I may not see that because of the fact that it's only present in this particular frequency band. And so that's why we have to be careful that when we don't see anything, it does not mean that there's nothing there. It may mean that there's something there, but it's just covered with noise. And so, but if I look at each of the frequency bands specifically, I may actually see it.
Great. Thank you. Is there any other question? So if there's no more questions, Hernando, can I share my screen again?
Yes, I will stop sharing now.
So, okay, so before I let you go, so the next seminar will be July 16 from 12 p.m. to 1 p.m. Given by Dana Tudor School from University of Pittsburgh. And then Dana will talk about PET imaging, which is another type of neuroimaging and a measure brain metabolism. Please join us next time as well. And then thank you so much, Hernando, and thank you all for coming.
Thank you. Thank you all. Cheers. Bye-bye.
Thank you. Bye.
Thank you.